Hi, in this video we're going to switch to code for rounding. So let's go ahead and take a look at that. Now the round function is built into Python. So it's not in the math library, in the math module, it's just built in. So it's right there. You can do a help on it if you want, or just refer to the last video where we talked extensively about the round function. So let's just go ahead and do some examples. So I want to talk about round when we only specify a single parameter, which is the number we want to round. Then this means that our n digits, or n as we had in the previous video, defaults to 0. And so when we do that, we'll get a will have a value. It should be 2, right? We're going to round 1.9 to the closest integer, which should be 2. But I also want to look at the type of a. And as you can see, a got rounded to 2, and the type of a was an int, right? So it actually cast 1.9 and returned a 2 integer type. That's not the same thing that happens if you were to say round 1.9 and then make n equal to 0, right? Now it's the same thing. It's still going to round 1.9 to 2. But because we've specified the second parameter, it's going to keep the type, the type that gets returned will be the type that was passed in. Right? So that's the only difference between those two variants. It doesn't really matter because of the polymorphism. We don't care a whole lot, and because of the non-static typing, we don't care a whole lot about whether this is an int or a float, but it's still good to know that that's happening. All right, so let's go ahead and start looking at positive n's, right? So in other words, I want to look at n greater than 0 kind of examples. And let's just go ahead and do this. Round 1.8888, comma 3, that means we're going to round to 3 digits after the decimal point, or, well, that's probably easier to understand, we're going to round to the closest multiple of 10 to the negative 3, right? To the closest multiple of 0.001, in other words. And so I want to show you the progression this way. So we'll take the same number, round to 2, and then we'll round 1.8888 to 1, and we can even round 1.8888 to 0, right, which we've seen before. So there you go, right? We round to the third, so we keep basically 3 digits after the decimal point. Here we kept 2, here 1, and here 0, right? They're just multiples of 10 to the negative 3, right? This last digit here is a multiple of 10 to the negative 3. 1.89, that 9, is a multiple of 10 to the negative 2, and so on. So that's for positive. Now we can also have negative values for n, and this is where you may not be used to that. So let's take a look at it. And so we'll keep for n less than 0, okay? And let's try this. Now I'm going to use a slightly different number because now we're going to be rounding to the left of the decimal point. So I want to use a bigger number than 1 point something. So let's use 888.88. And we'll round that to 1 after the decimal point. I just want to show you the progression. Then we'll round 888.88 to 0. Okay. I'm going to use my line continuation. Remember that from one of the earlier videos. And then we're going to do round 888.88. Now let's start with the negatives. Negative 1, round 888.88. Negative 2, round 888.88. Negative 3. And for good measure, we'll throw in as well 888.88 negative 4. Okay? And we'll see what happens. All right. So, 888.9. Right? That's because it was 1 after the decimal point. 0, 888.88, right? It just rounded to the closest multiple of 10 to the 0, 10 to the negative 0, which is 1, so the closest integer. Now look here. When we switch to negative numbers, it's rounding this number to the closest multiple of 10 to the 1, which is 10. So it's rounding to the closest multiple of 10. Well, the closest multiple of 10 to this number is 890. This one, it's rounding to the closest multiple of 10 to the negative 2, which is 10 to the 2, which is 100. So to the closest multiple of 100. Well, the closest multiple of 100 to 888 is 900. Now, what about this one? We're looking to round 10 to the negative 3. So 10 to the 3 is 1,000. To the closest multiple of 1,000. Well, the closest multiple of 1,000 is 888.88. Now, what about this last one? Why is it suddenly 0? Well, what are we doing here? We're looking at rounding 888.88 to the closest multiple of 10 to the 4, right? Which is 10,000. Well, 888 is closer to 0, which is a multiple of 10,000, than 10,000 is. Now, if we're done round something that was a little closer to 10,000, let's say 9,800. Now, if we do that, then we'll get 10,000, right? But if we do something that's smaller, that's closer to 0, then we'll get 0. Right? Remember, it's rounding to the closest multiple. Okay, so the next thing I want to talk about are ties. So we really haven't seen that in the code yet. I've purposely left that out. So let's go ahead and take a look at what happens when we have ties when we're rounding. And what I mean by ties is that we're rounding to the closest multiple, remember, of some power of 10, and the two closest multiples are actually equidistant. So we have a tie and we need some rule to do tie breaking. So we can take a look at this example. Let's say 1.25. Now, we would expect this to round up to 1.3, but Python actually rounds that down to 1.2, right? And however, if we round 1.35, it rounds to 1.4, right? Which is, well, what we would have expected. What's happening here, as we discussed in the last video, is Banker's rounding. We're always rounding to the closest even digit, right? Or the closest multiple that has an even least significant digit, to be more precise, in the case of ties. So with 1.25 and with a power of 10 to the negative 1, in other words, the closest multiple of 0.1, well, we have either 1.3 or 1.4, right? Sorry, 1.2 or 1.3. So 1.2 has an even least significant digit, and 1.3 has an odd least significant digit. So we're going to pick 1.2. However, in the case of 1.35, which is between 1.3 and 1.4, well, 1.4, okay, it's equidistant between the two, and 1.4 has an even least significant digit. So we're going to pick 1.4. And this also works with negative numbers. So if we do negative 1.25 and we do negative 1.35, you'll notice that we get the same thing. It rounds to the closest multiple of 0.1, and in the event of a tie, it picks the one that has an even least significant digit. So 2 in this case and 4 in the case of negative 1.35. So that's called Banker's rounding. We discussed that in the last video in some detail, and that's really the kind of the default rounding that we have in Python and in many other languages as well. It has less bias, as we saw, than the rounding that we're used to, which is called rounding away from 0. We're always rounding away from 0. So 1.25 rounds up to 1.3, and negative 1.25 will round down to negative 1.3. In both cases, we're rounding away from 0. So that's why it's called rounding to the closest with ties away from 0. Now, if you really want to implement that method, you're kind of on your own. It's not built into Python. You're going to have to do it yourself. And so we can do it this way. Now, when we get to decimals in some of the next videos, in the upcoming videos, that module does have all these different rounding techniques. So there we don't have to reinvent the wheel. But for floats, however, we're left with this round function. We don't have anything else. We don't have a way of specifying a different rounding mechanism. So we kind of have to do it ourselves. Again, I'll refer you back to the previous video if you haven't seen it. So let's go ahead and just write it ourselves. Now, a common technique, right? I cannot write a function called round because it's already defined. So, I mean, yes, I can, but the problem is that now in this current module, when I call round, it's always going to call my function round, right? So let's try this. let's say something really stupid, right? It returns a string. So now if I say round 10.5, it returns A. That's really not what I wanted, right? So I'm going to restart the kernel. I want to get rid of this. I don't want to redefine round. So instead what I'm going to do is I'm going to call it underscore round. That's a pretty common way. If you're going to be using a function name that would shadow a built-in function, then you just put an underscore in front of it. And so it's still not the same thing. It's differentiated, but the name is still the same. So I want to keep it as round, right? But, you know, maybe that's not what you want to do. Maybe you want to say round ties away from 0. You can certainly do that as well. I don't want to have to write that every time I call the round function. So I'm just going to call it underscore round. And now this is only going to round to an integral value. Okay, so this technique only works for rounding up, you know, to an integral value. So from math import, we need the copy sign, right? We need that copy sign method that's in the math module. And then remember we had that slightly simplified formula. We're going to say x plus 0.5 times copy sign 1x. Okay, so that's our round function. And there was a slightly longer way of doing it as well. If you remember from the last video, I'm only going to show you this method here. So now if we call round 1.5, that's going to be our previous built-in method, right? The round to closest with ties to the even least significant digit value. And then we'll also round 1.5 with our round function. And what happens? Well, in both cases, we round it up to 2, and that's expected because 1.5 is between 1 and 2. 2 has, so it's equidistant, and 2 is the one with the least significant even digit, right? And then 1.5, we round away from 0, so that should go to 2. Now we can try that again with this time 2.5, and we'll call our function 2.5. Okay, so now here what we expect and what we get, well, 2.5 is between 2 and 3. It's equidistant, it's a tie, so as a tiebreaker, we pick the one that has an even least significant digit. Well, 2 is even, 3 is odd, so we picked 2. So round 2.5 returns 2. But our method that rounds away from 0 returned 3. And so that worked correctly. And the same thing will happen if we deal with negative numbers. Let's put that in. As you can see, negative 1.5, both methods rounded to negative 2. And in this case here, round negative 2.5 also rounded to negative 2, same as the negative 1.5 over here. But our round method rounds away from 0 always, and so we rounded to negative 3. All right, thanks for watching, and I'll see you in the next video.